Hello everyone, how are you? I hope this video tutorial finds you all good and healthy. I welcome you all in this video tutorial on modeling whole molecule disorder in azulene about the crystallographic inversion center. The crystallographic programs used are SHELXT and SHELXL. These programs are available free of charge for the academic users. The necessary files required for the refinement are used with permission of International Union of Crystallography and Professor B. Dietrich. If you are interested about the more detail of the molecule, its chemistry and crystallography, I recommend the article Azulene Revisited, Solid State Structure, Invariant Modeling and Lattice Energy Minimization of a Classical Example of Disorder. Acta Crystallographica, Section B. So before going to the refinement part, let's have a quick look about the structure of the azulene. Azulene with molecular formula C10H8 having a 5-membered ring fused with a 7-membered ring. It is an aromatic molecule having 10 pi electrons. For simple representation of the molecule, to understand the crystal packing and symmetry in a better way, I am omitting the double bonds and I am representing simply a 7-membered ring fused with a 5-membered ring. Then come to the azulene disorder. How disorder arises in the azulene. This arises due to the different orientation of the molecule during the crystal packing. Suppose this is the orientation number 1 of the molecule and this is the orientation number 2. So during crystal packing, one orientation lies above the orientation like this, and a crystallographic inversion center represented by the purple dot here arises in the molecule. So the inversion center is a crystallographic symmetry and not a molecular symmetry. So now come to the refinement part. So at this point, we are going to join the refinement. Up to now, the structure solution using SHELXT, we are getting the space group P21 by C and initial structure like this. If you compare this moiety with azulene, it doesn't make any sense and seems to be data of bad quality or not of good enough quality. But if you look at the I upon sigma, the crystal is diffracting up to 100 degree, 2 theta 100 degree. So it has a high resolution. Data is good and the goodness to fit is not actually around 1, it is away from 1, but completeness is very good. So the data is of good quality, but we are not getting the structure from the initial solution. So what I have to do, I am just going to refine. I am applying the weighing scheme and put acta on to generate the shape file, and I am going to refine it. Let's see what will happen. So after the first refinement, I am getting a Q peaks of around 14 electron here. So let's make it carbon and let's refine. The R factor is around 35%. Now it's dropped to the 21%. Now the maximum Q peak intensity is around 4.3 electron. It is here. Now it is very close to the earlier carbon atom, so it doesn't make any sense. But still, if you want to refine it by suppose carbon atom, then what will happen? The thermal will become too big and there is no further improvement in the R factor. So this should not be a carbon. Let's delete it. Now let's refine one more time. Now the shift value is around 0. Now we have only 14 carbon in the in the molecule. But here only 1, 2, 3, 4, 5, 6 and 7 carbon. Here 14. Because This is due to the symmetry of the molecule. Okay, let's now put these Q peaks off by pressing Ctrl Q, and now if you grow the molecule by typing grow or just pressing the Ctrl G by the keyboard, Ctrl G, it will grow like this. So from this molecule here, you can see a little bit, you can have a little bit idea about the structure. So here you can see this is a 5-membered ring fused with a 7-membered ring. From this side, a 5-membered ring fused in a 7-membered ring. So let's fuse first and let's name it systematically 1, 2, 3, 4, 5, 6, 7. And there are no more carbon atoms are possible in the M symmetric unit other than these 7 atoms. So name 1, and I'm going to sort, and if I'm going to edit my INS, then these 7 atoms are here: C1, C2, C3, C4, C5, C6 and C7. The thermal values are looking good. Let's refine it. Now this is not looking like an azulene molecule because the disorder is about the symmetry. So I have to grow the molecule just by pressing Ctrl G. Now you can see the molecule is grown, but it doesn't make any sense. So what I have to do, I have to model the disorder. Suppose I am choosing this as a 5-membered ring, so I have to delete these 4 atoms due to the symmetry. Just now it seems like an azulene ring, but there are no actually 10 carbon in the asymmetric unit. There are only 7, out of which I have deleted some carbon atom. So what I have to do first, I have to bring all these 10 carbon atom into the asymmetric unit, and then I have to define. For this, what I have to do, I will select all the carbon atom by pressing Ctrl A, and I will type part -1 minus C. What this means? Part -1 negative part number is for the symmetry equivalent or molecule on the special position, and -C brings the selected atoms into the asymmetric unit. Now press enter. Again select all the molecule. Since the molecule is disordered about the inversion center, it is only half occupied. So I will fix the occupancy to 0.5 only instead of 1 and press enter. Now if I am going to refine it, then you can see after a number of refinement, the R factor is dropped to some 11% and shift is 0, and maximum Q peaks is only 1.3 electron. Now the next step is anisotropic refinement by just typing anis, then hydrogen add, and then I am applying a restraint redo on the displacement parameter, and I am going to refine it. Yes. So after refinement, let's make the molecule formula. The R factor is down to 6.25% from 11%, and it further dropped to 5.57%. Let's refine one more time. Now the shift is almost 0 and the R factor is quite reasonable, and the F observed versus X sigma graph is looking very nice. Now the refinement is over. So this is the way in which you can tackle the whole molecule disorder. So if I press Ctrl Q, and these are the Q peaks, and I put the map on, then you can see the electron densities on the bonds, not around the atoms. So disorder is resolved here, and if I try Control G or just grow the molecule, now if I put the Q-peak off, then you can see these two orientations. First orientation here and the second orientation here, and here the crystallographic inversion center. So this is the one way to tackle the disorder. The second way is using the fragment DB. So let's do the second way. So I am joining the refinement from the same place, and I am going to delete these 4 atoms, and this is a azonil molecule. Now I don't want to use part -1 or part -C. I can use some other way to model this disorder. For this, I will go to the fragment DB, and I am searching for the fragment azulene. Here azulene user, since it is not originally present in the database, I put it later as a database, so there is a name user behind this azulene. So just select this one. Now the part should be -1 because the disorder is about the special position inversion center, so it is part -1, negative part number. Free variable I am using 1, and occupancy is of course not 1, it is 0.5. So now it is 10.5, and I am going to replace the earlier molecule, so I am using the replace mode, and I am going to fit. For fitting, choose any 3 atoms. This atom should be here, this atom should be here. So by selecting only 2 atoms, the molecule is looking good. Suppose this atom should be there. Now you can see it is almost fitted very nicely. Now press escape and press refine for Control R. Now you can see the R factor is around 11%, and there are 2 different orientations because I am fitting on a ground structure. That's why I am getting the 2 different orientation here. If I am going to type fuse, I will left with only 1 orientation. Now refine, and next step is anisotropic refinement, then hydrogen add, and then redo, and you can see this carbon atom is taking 2 hydrogen, which is not reasonable. Just delete it, select this one and type H add 43, and it will add the 1 hydrogen. Now refine it by just pressing Ctrl R, and you will get the R factor is around 6.3%. Refine one more time until the shift gets stabilized. Okay, let's come to work, and then everything seems to be nice. Let's increase the cycle to 20 for the easy and quick convergence. It is fluctuating a little bit, but okay, it will settle down. Yes, this carbon atom is fluctuating. Okay, no problem. Refine some more times, it will definitely get 0. Yes, it's now 0. The goof value is little bit higher than 1. This is not a disorder, this is due to some other reason. And now the F observer versus F calculated graph is now very nice looking, and it's complete the refinement parts. Hope it will helpful, and thanks for watching the video.